Welcome to Suchitra's statistics classes. Today we are going to discuss about Poisson distribution. In this session, we are going to discuss definition of Poisson distribution and its moments. The number of suicide in a day in a particular area, say city, street, etc. The number of deaths from rare diseases. Using these two examples, we are going to identify the situation of Poisson distribution. Here, the outcomes are dichotomous, either occurrence or non-occurrence, with a small probability of occurrence or success. So, the probability of occurrence is very small in these two cases. Number of deaths from rare diseases, number of suicide in a day in a particular area, etc. The probability of occurrence is very, very small. Being rare event, probability of occurrence P is very small, and the repetition of the experiment N can extend to infinity or large. That is, N tends to infinity. This type of events discovered by Simon Denis Poisson in 1837, hence named Poisson distribution. This is called laws of rare events. So, we can frame the PDF of this type of event as a limiting form of binomial distribution. Now let us derive the PDF as a limiting form of binomial distribution. So the conditions are: the probability of success P is very small, that is P tends to 0. The number of trials is very large, that is N tends to infinity, and NP is equal to lambda, a finite positive constant. What is NP in binomial distribution? NP is the mean. So, mean lambda, a finite positive constant. This approximation is suitable if P less than 0.05 and N greater than 100. The Poisson distribution can also be applied to a class of binomial events in which neither P nor N are known, but their product lambda is known or can be estimated. What is the PDF of binomial distribution? F of x is NCX, P raised to x, Q raised to n minus x. X varies from 0 to n. Q plus P equal to 1 equal to 0 elsewhere. So, let us rewrite Q as 1 minus P. So, we have f of x equal to NCX, P raised to x, 1 minus P raised to n minus x. And rewrite for NCX. What is NCX? N into n minus 1 into n minus 2, etc. N minus x minus 1 divided by x factorial. Instead of P, write lambda by n. Since we know NP is lambda, so f of x becomes this one. Then, what's the next step is take n outside from n minus 1, n minus 2, n minus x minus in this format. When we take n outside from n minus 1, we will have n into 1 minus 1 by n. When we take n outside from n minus 2, we will have n into 1 minus 2 by n, etc. When we are taking a n outside from n minus x minus 1, we will have n into 1 minus x minus 1 by n. So, altogether we have 1, 2, 3, 4, etc. up to xn. So, we can write that as n raised to x into 1 minus 1 by n into 1 minus 2 by n, etc. 1 minus x minus 1 by n divided by x factorial. And lambda by n all raised to x can be rewritten as lambda raised to x divided by n raised to x. 1 minus lambda by n raised to n minus x as 1 minus lambda by n all raised to n divided by 1 minus lambda by n all raised to x. This n raised to x and this n raised to x get cancelled. 1 minus 1 by n into 1 minus 2 by n, etc. 1 minus x minus 1 by n into lambda raised to x by x factorial. 1 minus lambda by n raised to n divided by 1 minus lambda by n raised to x. As n tends to infinity, that is the another condition we are going to apply to binomial. As n tends to infinity, limit n tends to infinity f of x is equal to limit n tends to infinity 1 minus 1 by n into 1 minus 2 by n, etc. 1 minus x minus 1 by n lambda raised to x by x factorial into 1 minus lambda by n all raised to n divided by 1 minus lambda by n all raised to x. And we know this result. Limit n tends to infinity 1 minus x by n is equal to 1. And limit n tends to infinity 1 minus lambda by n all raised to x is also equal to 1. And limit n tends to infinity 1 minus lambda by n all raised to n is equal to e raised minus lambda. So, when we are applying these results in this one, this term together, limit n tends to infinity 1 minus 1 by n, etc. 1 minus x minus 1 by n is equal becomes 1. And limit n tends to infinity lambda by n raised to x also is equal to 1. And limit n tends to infinity 1 minus lambda by n all raised to n. That is, limit of this one is equal to e raised minus lambda. So what we are getting? F of x is equal to lambda raised to x by x factorial e raised to minus lambda. X varies from 0, 1, 2, 3, etc. up to infinity. So this is the probability density function of a Poisson distribution, which is treated as the limiting form of a binomial distribution. Now let us define a discrete random variable with PDF f of x equal to lambda raised to x by x factorial e raised to minus lambda. X varies from 0 to infinity and equal to 0 elsewhere is said to follow a Poisson distribution with the parameter lambda. And it is denoted by x tends to p lambda. The cumulative distribution function capital F of x is equal to probability of capital X less than or equal to small x is equal to 0 for x less than 0 equal to summation 0 to x e raised to minus lambda lambda raised to x by x factorial for 0 less than or equal to x less than or equal to infinity and equal to 1 for x greater than or equal to infinity. Now let us discuss about the moments. Rth row moment mu r dash is expectation of x raised to r. Since x is a discrete random variable, mu r dash is summation over x raised to r f of x. So mu r dash we can write as summation 0 to infinity x raised to r lambda raised to x by x factorial e raised to minus lambda. So mu 1 dash is equal to, put r equal to 1. summation 0 to infinity x lambda raised to x by x factorial into e raised to minus lambda. Take this e raised to minus lambda outside and x by x factorial as 1 by x minus 1 factorial into lambda raised to x. So we are getting mu1 dash as e raised to minus lambda. Instead of 0 to infinity, we will write summation from 1 to infinity. Since 0 minus 1 is a negative number, it is not applicable to factorials. Mu1 dash equal to e raised minus lambda summation 1 to infinity lambda raised to x divided by x minus 1 factorial. So what we are going to do? We are going to take a lambda outside from this lambda raised to x. So we are getting a lambda and lambda raised to x minus 1 here. And summation 1 to infinity lambda raised to x minus 1 by x minus 1 factorial is a raised to lambda, or using this result. So what we are getting? Lambda e raised minus lambda into e raised lambda, which is equal to lambda. Mu2 dash equal to expectation of x square equal to summation 0 to infinity x square lambda raised to x by x factorial e raised to minus lambda. We know that we can rewrite x square as x into x minus 1 plus x. After rewriting that, remove the bracket. So what we are getting is this expression. We know that this second expression is nothing but mu1 dash, which is equal to lambda. Then in the first expression, x into x minus 1 divided by x factorial can be rewritten as 1 by x minus 2 factorial. So we are getting this expression as e raised to minus lambda, taking this e raised minus lambda outside, a lambda square from this lambda raised to x. So the rest we have lambda raised to x minus 2 divided by x minus 2 factorial plus lambda from this expression. And we know that summation 2 to infinity lambda raised to x minus 2 by x minus 2 factorial is equal to e raised to lambda. Here we rewrite summation from 2 to infinity instead of 0 to infinity. That is lambda square plus lambda. So mu2 dash is equal to lambda square plus lambda. Therefore, variance mu2 is equal to mu2 dash minus mu1 dash square is equal to lambda square plus lambda minus lambda square, which is equal to lambda. So mu1 dash is equal to lambda as well as mu2 is equal to lambda. Then let us think about mu3 dash. Mu3 dash is e of x cube is equal to summation 0 to infinity x cube lambda raised to x by x factorial into e raised to minus lambda. We know that we can rewrite x cube as this expression. Applying that expression in this mu3 dash, we are getting mu3 dash as summation 0 to infinity x into x minus 1 into x minus 2 plus 3x square minus 2x into lambda raised to x by x factorial into e raised to minus lambda. Removing the brackets, we are getting this result. And take 3 outside from the summation and 2 outside from this summation and rewriting x into x minus 1 into x minus 2 divided by x factorial as x minus 3 factorial, and take a lambda cube outside and e raised to minus lambda outside, we are getting lambda cubed e raised to minus lambda summation from 3 to infinity lambda raised to x minus 3 divided by x minus 3 factorial plus 3 into summation 0 to infinity x square lambda raised to x by x factorial real into e raised to minus lambda minus 2 into summation 0 to infinity x lambda raised to x by x factorial e raised to minus lambda. This expression is mu2 dash and this expression is mu1 dash and this is e raised to lambda. Therefore, mu3 dash is equal to this expression. Simplifying, we are getting lambda cube plus 3 lambda square plus lambda. And what is mu3? Mu3 is obtained using this one. Therefore, mu3 is equal to lambda, applying the value for mu3 dash, mu2 dash and mu1 dash. Then mu4 dash. We can find mu4 dash in the similar format by rewriting x raised to 4 as x into x minus 1 into x minus 2 into x minus 3 plus 6x cube minus 11x square plus 6x. And removing the brackets and proceeding in the previous format, we are getting mu4 dash is lambda raised to 4 plus 6 lambda cube plus 7 lambda square plus lambda. Therefore, mu4, using the expression, we can find mu4 as 3 lambda square plus lambda. So, for a Poisson distribution, mean is equal to variance is equal to third order central moment is equal to lambda. That is, mu1 dash is equal to mu2 is equal to mu3 equal to lambda and mu4 is 3 lambda square plus lambda. Then let us think about the measures of skewness. What is measures of skewness? Skewness measures departure from symmetry. How much the distribution is away from the symmetry. For that one, we are using the measures beta 1 and gamma 1. Beta 1 is mu3 square by mu2 cube, which is equal to 1 by lambda in this case, and gamma 1 is root beta 1, which is 1 by root lambda. For small values of lambda, gamma 1 is a positive quantity. That is, the distribution is positively skewed. For large values of lambda, gamma 1 tends to 0. That is, the Poisson distribution approaches a symmetrical distribution. Then measures of kurtosis. Kurtosis measures peakedness or flatness of a symmetric curve. And measures of kurtosis are beta 2 and gamma 2. Beta 2 is mu4 by mu2 square and gamma 2 is beta 2 minus 3. For small values of lambda, beta 2 is 3 plus a positive quantity. That is beta 2 greater than 3 and gamma 2 greater than 0. Therefore, Poisson distribution is leptokurtic. For large values of lambda, beta 2 tends to 3 and gamma 2 tends to 0. That is, Poisson distribution approaches a mesokurtic curve. The things studied from this class are definition, a discrete random variable with PDF, f of x equal to lambda raised to x by x factorial into e raised to minus lambda, x varies from 0 to infinity or equal to 0 elsewhere is said to follow a Poisson distribution with parameter lambda. The cumulative distribution function capital F of x is P of capital X less than or equal to small x is equal to 0 for x less than 0 equal to summation 0 to x e raised minus lambda lambda raised to x by x factorial from the range 0 to infinity of x and equal to 1 for x greater than or equal to infinity. For a Poisson distribution, mean is equal to variance is equal to third order central moment, that is equal to lambda. Mu1 dash equal to mu2 equal to mu3 equal to lambda, and mu4 is equal to 3 lambda square plus lambda. So we will get measures of skewness beta 1 and gamma 1 like this, and measures of kurtosis as beta 2 and gamma 2 like this. And everything depends upon the value of lambda, and lambda is the one and only one parameter of Poisson distribution. Thank you for watching. If this is found to be useful, then like and subscribe Suchitra's statistics classes.